of the Capitol building to the YouTube community. Stay tuned to the end of the video to find out what this one Uber Super done a fantastic episodes. The Abbey and the Monastery. Below are the Great Hall. This place is near the top. Even if you don't think you're going to make the video, was the very top section and the transition between the base and the rest of the tower. I ended up making the base to tower. You might have noticed, but I'm just much. After a couple touch-ups, I copy and paste indents. To be completely honest, I remember back to a few minutes ago, each touch-ups I copy and pasted walls to give it a little more separation and punch. After a couple touch-ups, I copy and pasted the rectangular design onto the rest of the tower. The only rectangle that's different was the one at the very top on the south side, and instead of being 7 floors tall, it's only 4. At that point, the tower was done and the only thing left was the roof. My main reference was that obscure picture I took a year and a half ago. I noticed the very top balcony on the south side doesn't have any weather protection, so I removed the row of slabs above it. I then made a 9-block tall gray and green pillar, so I knew the max height that I could build. I extended the tower to its final height, fixed the shear wall, and kept going from there. I tried a bunch of different size combinations for the bays on the south side, and eventually settled on 3 glass and 1 pillar. I added the very top section, added some HVAC equipment, and the green roof. Back down to the large windows at the top, I added a little guardrail and some carpet to mask the visible floor plan. If you look closely at this picture, you can see that the top balcony here doesn't have anything above it, and the glass behind it is just set back and continues upwards. Once again, I used the trick with the alternating glass and added some vertical iron bars. Once that was done, I finished up the lower roof section, finished the shear wall, and added the lowest green roof section. I split up the sections and added some greenery to it. I used a combination of grass, tall grass, ferns, 2-leaf variants, and some white and pink flowers just to keep the color palette simple. Great, now the build looks pretty, so let's move on to the mid-section of the roof. I extended it across, added some skylights for the stairwell, and added the glass across the side of the midsection. For the final touch, I finished the green roof and filled in the greenery. Ladies and gentlemen, just like that, the tower was complete. I hope you were able to tell that this build and video took a long time to plan and make. I would really appreciate it if you'd leave a like so the YouTube algorithm can recommend this video to more people. If this video gets 10,000 likes, I'll come back on this server and build either another skyscraper or help out with the CN Tower once the upgrade to 1.17 happens. Once again, thanks for watching, and don't forget to check out Game Fruit Pulp's channel using the link in the description. Why do we need sustainable buildings? The short answer is climate change. Human-made pollution is the cause of rising levels of greenhouse gases in the atmosphere. The average temperature of the Earth is increasing because heat is struggling to escape. This is called the greenhouse effect. Climate change will have worldwide effects such as changes in precipitation patterns, more droughts and heat waves, increased intensity of storms and hurricanes, and a rise in sea level. A commonly asked question is, why don't we focus on cars and planes rather than buildings? This is a very fair question. Buildings account for more than 40% of primary energy consumption in the United States and EU, which is more than the entire transportation industry in those countries. Since we still have quite a ways to go to hit completely renewable energy sources, we need to reduce energy usage as much as possible. The 2 main types of energy are embodied energy and ongoing energy usage. Embodied energy is the total amount of energy used to get the building from an idea all the way to handing over the keys to the client. This includes the supply chain needed to mine, create, transport, and construct each part of the building. Before we get too far into the video, I just want to show off my new architectural clothing line. I think it's pretty cool. Anyway, let's quickly go over how buildings work, because it isn't as easy as having a floor, walls, and a roof. A building works together as an integrated system. First, you have the building envelope, which includes partition walls, also known as non-load-bearing walls, windows, doors, floors, and the roof. Next, you have the elements that actually hold the building up, the structure. This includes footings, foundations, pile drivers for tall buildings, columns, girders, joists, wood studs, shear walls, tension members, frames or trusses, and a whole bunch more. After that, you have mechanical systems. The main elements of this system are heating, ventilation, and air conditioning, also referred to as HVAC. The next category is electrical systems, which includes lights and energy usage. The final system type is sensors. This includes alarms, security systems, communication systems, and building automation. There are different types of energy goals. The first is carbon reduction, which means you are simply taking steps to reduce the carbon footprint. The second is carbon neutral, where the idea here is to offset carbon emissions by using sustainability practices that have an overall net zero carbon footprint. The third type, which is the hardest to achieve, is regenerative, which means the building has an overall positive environmental impact. There are different types of green building rating systems, such as LEED, LBC, and many more. LEED is very common and uses categories like sustainable sites, water efficiency, energy and atmosphere, materials and resources, indoor environment quality, and location and transportation. The pre-design phase is incredibly important. Choosing the wrong site or making the wrong decision during this phase will have a large effect on the overall environmental impact. The type of site is important. It is more environmentally friendly if you are building on a site that is not new land. For example, it is better to build on an area of land that is currently an old parking lot, rather than cut down trees and build in a forest. This prevents the destruction of natural areas and habitats. Wherever possible, you should try and integrate the landscape and ecosystem into or around your building. Another option is to renovate or add an extension to an existing building rather than demolish it and make a new one. The location of the site relative to nearby cities is also important. This affects the amount of carbon emitted by construction workers, visitors, and occupants of the building when traveling back and forth between a major urban center. Connection to public transportation should be a top priority. The more building occupants that use public transportation, the better it is for the environment. Having this site along a major bus route or train line will have overall easier access than if you had to drive an hour by car to get there. An important note before we go in depth: passive means something happens on its own. Active means there is some sort of human interaction that is physically intervening. Passive is better when properly calculated because our goal is to reduce the active amounts as much as possible to reduce the overall energy consumption of the building. Let's get into passive design and how we can use these concepts to design buildings. There's a really cool concept known as a wind catcher. It's commonly used in North Africa and in countries around the Persian Gulf where they have a very warm climate. To cool down the building, the basic idea is to force cool, moving air into the lower or underground sections. Hot air rises, so this cool air will force the warmer air upwards and out through an opening, resulting in natural airflow, cooling, and ventilation. To cool your building, you may also incorporate shade or window overhangs. Strategically placed walls, windows, and overhangs makes it so that the sun does not overheat the building. In the northern hemisphere in the winter, the sun follows a much lower path throughout the day, closer to the horizon. However, in the summer, the sun's path goes much higher into the sky. Therefore, to keep the sun out during the summer and in during the winter, we need to block the sun when it is higher in the sky using overhangs. If, for example, you are designing a building where this might not be possible, sunshades may be used, such as in high-rises. In the northern hemisphere, to passively heat your building, you need southeast facing windows. The sun rises in the east and sets in the west. Every building has a thermal mass. Thermal mass is simply the ability of the building to retain heat over a period of time. The time delay is a measure of how long after the external temperature changes that the internal temperature of the building also changes. This being said, with southeast facing windows, your building will be heated by the sun in the morning. Buildings are colder during the night, so you will want to heat it up as soon as the sun comes up. If you were to have southwest facing windows instead, your building would not be heated in the morning, forcing you to use active heating, and then you would get the afternoon sun after your building is already heated up. Now, you have a problem, since you don't actually want the heat from the afternoon sun. Your building is already warm, and since you are getting more heat, you need to actively cool it down in the afternoon. This doesn't mean use only southeast facing windows, but any large, open windows should be in that direction. You can absolutely have windows on every side of the building, just be conscious of the sizes. If you're designing for a climate that can be both cold in the winter and hot in the summer, you need to take the cooling effects into account as well. There is a balance point that is different for every building, relating to the size and positioning of your windows and taking the rest of the passive and active design elements into account. We can get a good feel for what the design may need to include by calculating values known as heating degree days and cooling degree days. The basic idea of these values is to have a reference for how much you will need to heat or cool a building throughout the year. If we take a look at igloos, we can see that passive heating of buildings has been used for a long time. Igloos use a similar technique as the wind catchers, but they want the warm air to stay inside rather than be pushed outside. The dome of the igloo is elevated above the entryway. Cold air moves down into the lowered entry and forces any warm air to move upwards, getting trapped inside the dome of the igloo. The igloo still has a vent, but it is obviously much smaller than the vents used in the wind catchers. Today, insulation is the most common way of passively retaining heat. The issue is finding the balance of windows versus walls. Windows generally lose a lot more heat than walls. R values are a measurement of how well heat is retained. A higher R value means heat is lost more slowly. There are actually plenty of ways to change the R value of a window. The first way is you can vary the type of glass to let more or less UV, infrared, and visible light in, which will change the rate of heat transfer through the window. The second way is by having one or two chambers between the glass panes filled with either air or a type of gas to slow the rate of heat transfer. Third is the type of gas between the glass panes. Different noble gases have different rates of heat transfer. One of the most commonly used gases in windows is argon. If you've taken high school chemistry, you'll know that noble gases are stable and inert. Fourth is by choosing a material with sufficient thermal resistance for the frame and spacers. And finally, the fifth way is to have a tight window that is of high build quality. While we are on the topic of windows, let's talk about passive lighting. Natural sunlight is fantastic for any building, but we need to be careful during the design. As previously discussed, you need to be careful with window placement and the size of windows to prevent overheating or overcooling. At the point where passive design isn't enough, we are forced to use active design. This is where a key part of building science comes in: building automation. The idea here is to automatically heat, cool, ventilate, or change any sort of mechanical or electrical equipment, either as a part of the entire building or a single room. Whenever possible, energy-efficient mechanical equipment is preferred. If you're designing a medium or large building, consider using an HVAC system that is able to individually control rooms rather than just the entire building at once. By doing this, the building occupants can have whatever temperature they want. With building automation, you may choose to use motion sensors. If the sensors detect that no one is in the room, it will automatically lower the thermostat and dim the lights to save energy. Ground source heat pumps are a great alternative to traditional heating methods. The basic idea is to push warm air outside during the summer and pull heat from the ground inside during the winter. Rainwater collection and water filtering is a key component of green building design. If you don't want to use composting toilets, the least you can do is use rainwater rather than potable water provided by the hydro network. You may choose to filter the rainwater to be used as drinking water. Remember, this isn't a one or the other type of situation. Most buildings that collect rainwater are also hooked up to the hydro network for when the rain isn't sufficient. The type of material you choose can have a big impact on the amount of embodied carbon. Most large commercial buildings or high-rises use steel framing. This makes sense since steel is incredibly tough. The issue is that steel requires an insane amount of energy to mine, manufacture, and transport to wherever it's going. It is also very expensive, especially when compared with concrete or wood. A way to offset the carbon footprint is to use local materials. If we look at the west coast of Canada and British Columbia, we might notice that a lot of buildings use wood that has an orange hue. This type of wood is likely Douglas fir, a type of tree commonly found throughout the province. If your building requires concrete, consider using a special type of concrete called carbon-negative concrete. Indoor green walls are a great addition to any space. Not only do they make the space look nice, the plants actually provide fresh air to the occupants, reduce noise, and increase the value of your building. You could even argue that it makes people more productive. Green roofs are fantastic. The soil on the roof preserves the building's heat, plus it cleans the air and looks great. Solar panels, also known as photovoltaics, are common in high-performance buildings, but can look pretty ugly if designed improperly. This is where building-integrated photovoltaics come into play. If you're clever, you can hide these solar panels in your design either on the roof or as part of the side of the building. There are optimal angles for solar panels, and it all depends on where in the world you live. As you can tell, there's a lot of elements to green building design. I hope you were able to learn a thing or two from this video. If you want another video on a specific topic, hit the like button for the YouTube algorithm and leave a comment telling me what you want me to make in the future. Check out the Andean Skyline Collection, a minimalist architectural clothing line with zero branding. Hi there, my name is Matt, and I work as an architectural engineer in Canada. In this video, we will be building the condo tower behind me. Now, before we get started, if you could press the like button for the YouTube algorithm, it would really help me out and makes it so that I can make more videos like this in the future. I would also ask that while watching, if you enjoy this content, please consider subscribing. Hi, my name is Matt, and I work as an architectural engineer in Canada. In this video, we will be designing a realistic high-rise in Minecraft. Now, before we get started, if you could hit the like button for the YouTube algorithm, it makes it so that I can make more videos like this in the future. I would also ask that while watching, if you enjoy this content, please consider subscribing. You've probably noticed that high-rises are generally found in big cities. This is because the higher the density, the more expensive the land becomes to buy. Since the goal of developers is to make as much money as possible, they maximize this expensive land by building upwards. This doesn't necessarily mean that heavily populated cities will be mostly high-rises. It depends on the land area around it. Let's look at Los Angeles. Los Angeles has a population of almost 4 million people in 2018. If we look at LA, we can see it is very spread out because the only natural features constraining it are the ocean in the west and south and mountains in the north. The majority of Los Angeles is on a relatively flat area and has very little physical constraints. Now, let's compare with one of the most well-known cities in the world, New York City. Specifically, the island of Manhattan. Manhattan alone has a population of 1.63 million in 2019, but is significantly more constrained, resulting in many more skyscrapers. When we compare New York and Los Angeles side by side, we can see that New York City has a much taller skyline. Loads are gravity loads, which include dead loads and live loads. The dead load accounts for the weight of the building and any permanent equipment. The live load is the weight of anything that does not stay in the building, such as the occupants or workers. It's very important that we account for earthquake and wind loads in high-rises. Not accounting for these two types of loads can cause the building to sway back and forth to the point of making the occupants uncomfortable, or in the worst-case scenario, structural failure. To counteract these forces, we use tension members. Tension members are used all the time in buildings, usually in the form of diagonal cross bracing. Many buildings, however, will simply use reinforced concrete instead. These buildings are generally in zones that are not prone to earthquakes. Tuned mass dampers are used in extremely tall buildings to prevent the top of skyscrapers from swaying. Engineers suspend a large, heavy ball near the top of a tower. This ball is generally made of concrete or made of steel and filled with water. It has a very large mass and therefore a lot of inertia. This means that if wind or earthquake loads push the building to one side, the tuned mass damper will significantly decrease the movement. In very tall buildings, holes will sometimes be incorporated into the architectural design to reduce wind loads. 432 Park Avenue in New York City is one example of this. Designers are also well aware that wind may cause vortices behind a tower. These vortices cause a region of low pressure which will try and move the building. Engineers and architects will often stagger floors as the tower goes up to prevent this, such as in the Burj Khalifa in Dubai. The final type of load is snow loads. We will discuss this later in the video. Foundations are very important, because any loads created by the skyscraper need to have a method of transferring to the ground. For this video, we are going to be focusing on the above ground section. We will be working with just a slab, but keep in mind that in real life, this foundation is not realistic. Another reason for the slab is because there is actually a high-speed rail station about 15 meters below the site. Real-life foundations are big holes dug into the ground and use footings and pile drivers to prevent the tower from tipping over. I would also like to point out that this video is being filmed in cubed pack, so some blocks may look different than default. Normally, I like to build point towers. Point towers are commonly found in Vancouver and are characterized by having row homes or commercial shops at the base. The actual tower itself is set back on top. In this video, we will not be making a point tower. We will only be using a simple base, more commonly found in New York City or Toronto. Well-designed towers will have a clearly defined base, middle section, and top. This base is usually 2 to 5 floors. This structure will create more texture and will make your builds look better due to the added complexity at the base. A general rule of thumb is to have it complex at the bottom and simple as you go up. A trick to make your build look taller is to have larger ceiling heights on the bottom floors and shorter for the upper ones. I generally recommend 6 to 7 tall ceilings for the first floor, 5 to 6 for the rest of the base floors, and 4 to 5 for the tower itself, with 2 blocks in between floors. For the placement of the tower, if you can, have it set back from the street so that you don't block sunlight. Most skyscrapers use reinforced concrete shear walls. You can think of the skyscraper's interior structure like a tree, with the shear wall being the trunk, the floors being the branches, and the exterior glass being the leaves. In a shear wall, you typically have the most important occupant elements of a building, the elevator shafts and emergency stairs. For the first floor, we will have washrooms, a lobby area, mailroom, and a spot for security. I will be building this later off camera. I'm actually going to leave only the structural systems in place for the first 3 floors because I want to focus on the top section. It'll look a bit odd, but we'll fill it in later. Obviously you can't do this in real life, but this is Minecraft, so we can cheat the system a little bit. We are now going to move on to the architectural interior design. You need to assume that every floor is a single company. We are going to need an interior hallway, meeting rooms and offices, a lobby area with a reception desk, 2 washrooms per floor, and a kitchen or break room. Keep in mind that the floor plan is built around the shear wall. Off the shear wall, you will attach the floor and likely have smaller columns near the outside of the building for extra support. We are going to use interior walls to disguise these supports from the occupants. Now, we could go into calculations on how big these supports need to be, but that might be a little too hardcore for a Minecraft building video. In Minecraft, if you want to add a neat visual effect, you can add glowstone or beacons on the edge of the floor plan hidden underneath trapdoors for a neat glowing effect at night. For the exterior, we are going to add a glass facade to our building, also known as a curtain wall. Adding white glass panes as fins increases the structural efficiency of the glass and also adds texture to your facade. For this video, this is as complicated as the structural systems are going to get. In future videos, we might go into more complex topics. So for the exterior design, we're going to go with a mix of